Okay, so I did go into Canvas this morning. I opened up our last module. I also turned on all the assignments, although not all of them are visible to you at this time. So you can see what is left for us to cover in the class, both in assignments and chapters. So all that's opened up. And because we are a week and a couple days away from the end of the class already. Time flies. I can't believe how there just isn't enough time to cover everything. There just isn't. I mean, I've got a whole nother module and a whole bunch of other stuff that I don't even include. There's just that much stuff. So it is challenging for both of us, for me to try to squeeze it in and for you to try to absorb it. So I do understand both ends of the equation. Today we're going to finish up with our fuel system monitor, and then I also have an OBD2 scan tool PowerPoint, which kind of reiterates or goes over some of the stuff I covered on the video. Explains that a little bit, explains a little bit more of the nuts and bolts to it, also explains mode 6 a lot more, so we'll look at that. Then we're going to be getting into emissions, and that PowerPoint is the third PowerPoint in the section in Canvas, so the other PowerPoint is visible and is there. So we'll probably finish up on OBD2 framework today. I did open up the last discussion. The last discussion is in module 12. It is based on another article that I'm going to have you read. This one's called Diagnosing a Misfire. There's also a misfire diagnostic video that I just put on. That's a lab, extra credit lab, that shows me going through and how I determine why a cylinder is not firing correctly, causing a misfire. And so I go through how I eliminate things, and then how I finally come to the conclusion of where the problem is. So I do have one other optional lab that I may get up by the end of class. If I do, I'll get it up next week. And that's another video lab. That's where we're at with the class. Any questions before I get into the fuel system monitor? Okay. So our fuel system monitor, EPA requires the monitoring of the fuel system, and this goes back to the first OBD2 vehicles. How we have monitored it as far as accuracy and refined control certainly evolved over 25 years as technology has gotten better and more advanced, but the actual requirement hasn't changed. Just what used to be okay isn't so much okay. We've just really refined the standard and tightened that up as far as what is required for being clean. So what was clean in 96 is not necessarily clean in 2010, right? Technology has changed, standards have changed, and so on. A diagnostic system shall monitor the fuel delivery system's ability to provide compliance with emission standards. Continuously monitored whenever the engine is running in closed loop. In other words, whenever we're looking at the oxygen sensor and using the oxygen sensor for fuel control, we're monitoring how much fuel we're having to add or subtract from our base speed and load cells in order to keep the oxygen sensor operating in the correct voltage range. These can be an A or B type DTC. Normally we see these as a 2-trip or a B type DTC. Relies on fuel trim data directly and the O2 sensor indirectly. So since we know that the O2 sensor and fuel trim are closely related, if the O2 sensor is not acting correctly, fuel trim will respond trying to get it to function properly. So we know that fuel trim is both a response and a command with the O2 sensor, but fuel trim is what actually we're watching. We're watching the effort that it takes to have the O2 sensor move and function correctly. So fuel trim, we have short-term fuel trim, long-term fuel trim are what we use for our fuel trim monitor. Values are in percentage, or see plus or minus Percent means the percentage of fuel being added or the percentage of injector on time being changed. Usually plus or minus 10% is acceptable. So when we look at our fuel trim values are very important. So they're included in our freeze frame data. The data is shown as a percentage of injector on time, either positive or negative, with 0% being neutral. In other words, at 0%, we're using exactly the calculation that the engineers put in the base speed and load cell tables. Greater than 0% means the system is adding injector on time, and less than 0% means the system is subtracting injector on time. If you notice, I was very careful in my wording here. We're adding and subtracting injector on time, not necessarily adding and subtracting fuel. Okay. For example, if I have a fuel system that's supposed to operate at 40 psi, but there's only 30 psi, so the O2 sensors would indicate that we are having a lean condition. We would increase the amount of time that we're holding the injector open to get the oxygen sensor to say that we are back close to that stoichiometric ratio. But in reality, we haven't added any fuel. We're back to the same amount of fuel that we were supposed to have in our base calculations. It just took 10% longer injector on time in order to accomplish that, or 20% or whatever. So I want you to get out of your head that we're adding fuel. Yes, the intention of the computer is to add fuel through increasing on time, but it doesn't necessarily mean we're adding or subtracting fuel. And the reason why I point that out is it opens up other possibilities. Once you get out of the fact of, gee, why is it adding fuel? Why is it adding fuel? Was it adding fuel or is it adding on time? It's adding on time. It may not be adding any fuel. You might still be stoichiometric out the back, or even running lean out the back, even with additional injector on time. All it's doing is it's adjusting the injector on time to try to get us back to a stoichiometric ratio. And it just brings up other possibilities of things that can fail on the vehicle and get you thinking a little bit out of the box when you keep that in mind.
Sir Brian?
Yes.
If the injector is not adding fuel, so what does it do? Why does the monitor see it as just the injector is open and not
right.
fuel?
So by opening the injector longer, the intent is to allow more fuel to flow into the engine. So that's what it's doing, is it's allowing more fuel to flow through the injector by holding it open longer. But in reality, we may not be adding more fuel than what was originally required, because we may have low pressure, we may have a plugged injector, we may have other issues going on. So the computer's intent is to add more fuel, but we might not be adding fuel above what was originally required. We may just be getting back to even based on other issues.
So it's just on the ready mode.
Exactly. So it's really about increasing the on time. Yeah, and it is an interesting distinction, and I'm really spilling. Tim put this in the chat, and it is kind of splitting a really fine point, and that fine point may lead to some confusion at this point in your education. However, what I have found working on cars is that if I didn't understand that fine difference, there's cars I would not have fixed. Because if I just beat my head of it's adding fuel, it's adding fuel, it's adding fuel, instead of stepping back and going, no, it's adding on time. Why is it adding on time? What is it trying to accomplish? Why is this going on? Or taking away on time? It's adding the on time with the purpose of adding or subtracting fuel. Just in reality, it's not always doing that. And it just opens you up when the easy things aren't the problem, to kind of stepping back and going, what is actually happening here? What are we actually doing? And what possible failure could cause what I'm seeing to actually make sense? And I teach this concept when I do advanced diagnostic classes, and I have technicians that, you kind of see the light bulbs go off in the class because they've been chasing adding fuel or subtracting fuel for 10 or 20 years or longer. And when you really break it down to on time, you can see the light bulb go off, and you can see that's why I couldn't fix that car. That's why I struggled with that, was that difference in distinction. The other reason why I really emphasize that is when we think about changing percentage of something, it puts a lot more meaning in those fuel trim percentage numbers. It's not just some arbitrary percentage that it's a fuel trim percentage, but it's actually the percentage of the time that we're changing the amount of time we hold the injector open. So that also really, does it. So for example, I could have high positive fuel trim because I have excessive resistance in the power wire feeding the injectors. So I'm having to hold the injectors open longer to try to deliver the same amount of fuel. So because it's going to delay how soon they open up, and resistance, even 5 ohms changes injector opening time by about 7%. So I'm going to, deliver with just 5 ohms resistance. It affects, 7 ohms of fuel, and GM says 5 ohms is not a problem. But 7% of on time, that's a big on time, and we actually can measure that out and see that. We've done this. But if I'm chasing a car with a code says, P0171 fuel trim adaptation at lean limit, I'm looking for mass airflow sensors. I'm looking for vacuum leaks. I'm looking at all these things. Why is this car adding fuel? Why is this car adding fuel? Because I'm looking at, why would it be running lean? Why would it be running lean? Instead of stepping back going, why are we adding injector on time? Well, maybe there's a problem with the circuit where I have to hold it open longer just to keep it open the original amount of time, because of resistance in the circuit or resistance in the injector, things like that. So it allows you to kind of not get buried in the, it has to have a vacuum leak, it has to vacuum leak, or I put 3 mass airflow sensors in it, or I put 2 fuel pumps in it. It keeps you out of that just beating your head against the wall because, I'm trying to add fuel, Well, hold on a second. Let's think about what the computer's doing. What's it doing? And more importantly, how is the oxygen sensor operating with what we're doing? Is it still oscillating? It looks normal, or it's stoichiometric, because I might not have a gas analyzer, so I need to use the O2 sensors for that, which means the computer is doing the correction correctly. But if I don't have something allowing extra air in, then I have to look at why are we not delivering fuel with the engineered amount of on time. So so we tend to look at lean codes as we're getting extra air in or not measuring air, or I have a severe fuel delivery problem like a bad fuel pump or something like that, but we really don't think of that fine stuff about, wait a minute, where could we get? So that's why I make that distinction, because it is a real important distinction when you start getting into diagnosis.
Are you talking though, Brian, in this case, you would look at the low-hanging fruit things first, the mass airflow sensors, those kinds of stuff, and then when you don't see any other problems, that's when you start going down that hole of, okay, the on time is longer or whatever. Yeah,
exactly. Yeah, I mean, 80% of the time. Yeah, if 80% of the time, if I have a fuel trim coated idle, it's a vacuum leak on a mass airflow sensor car. It just is. Okay. But we know on speed density cars, a vacuum leak won't cause positive fuel trim. And we know that from doing different testing I did in different videos I did. So if I have a Honda in and it's setting a fuel trim coated idle for running lean, and I got good fuel pressure, I need to be able to go, wait a minute, why are we adding injector on time? Why are we, right? Because obviously it can't be a vacuum leak because it's a speed density system. So now I have to really start racking my brain, what could cause it? Because speed density systems don't fail lean, they fail rich. So in other words, if I have a hole in my vacuum line go to my map sensor, it's going to detect that as more load and dump more fuel. So cars with speed density, we normally see rich adaptation codes, 172 and 175. Where mass airflow sensor cars, we normally see lean adaptation codes, 171 and 174. So when you have the opposite of that, if I have a mass airflow sensor car with a rich code, those are extremely hard to diagnose. If I have a speed density car with a lean code, very hard to diagnose. And that's where this comes into play. Because all the simple low-hanging fruit, you don't even have a ladder or a hook. I mean, you're like, what the heck is going on here? These cars don't fail this way. And especially at idle, because if it's a fuel pump problem, we're going to see it off idle high demand, not at idle. So then you're really, what the heck is going on here? And understanding that it's on time. Okay, now let's start looking at things that are going to cause it not to deliver the right amount of fuel in that time, or do I have a bad sensor? Do I have some plugged injectors? And I've run across some really interesting vehicles, and I've written some interesting case studies on those types of issues. I had one case study I did where I have a car that is taking away fuel. The car is failing smog because it's running lean out the tailpipe. The oxygen sensor is good. It reads correctly when it tested. I mean, sees rich, sees lean. The short-term fuel trim and long-term fuel trim are responding to the oxygen sensor, and yet the car is running super lean out the tailpipe. And this car had already been to 2 shops that had parts put in it. And it's like, what the heck? The oxygen sensor is good. That's the eyes. The eyes are good, but yet the computer's taking away too much ejector on time. And the car's running lean and failing for high NOx. So it was a bit of a conundrum, and I had to kind of get out of the box and use this logic. And the thought I had is, I have one O2 sensor for 6 cylinders. Does it see all the cylinders the same? Well, of course it can't. So could I have one cylinder that might be flowing too much fuel, and then we're kicking other ones out to flow less fuel to balance it out? So I went in and started looking at each of the injectors individually, and I found that we had some bad injectors. I had an injector with a resistance problem causing excessive flow on 3 of the 6 injectors. But yet the computer, because that was the side the O2 sensor's on, the computer was backing everything off. So the side without the O2 sensor was running too lean, and that was causing the high NOx. But that was nothing is making sense car. But when I go back to, wait a minute, we're adjusting on time. The computer takes away on time based on what the O2 sensor sees. And we know we're running lean out the tailpipe, and we know the O2 sensor is good. So now you got to start thinking, why would the computer take away on time? Well, the O2 sensor sees all of the cylinders on that bank, not just one. It's an average. So now let me start looking to see, is everyone equal? And like I said, you get some interesting stuff, but that's a real world. Matter of fact, I just used that case study in a webinar I taught. And that I guess they liked enough, they want me to teach it again in September. They just put it on my schedule. So
Sir Brian, it's because it's showing average, it's not showing an error, right?
yeah,
Even though there are problems in one or the 2 cylinders. So you have to check every one of them,
right.
each cylinder.
Yeah. So let me see if I can pull this up real quick. Let's see. Yes.
But how would we know that if the sensor is showing no problem because it's reading the averages of the cylinder? How would we know to check each and every one? Because there is another code that is showing a problem.
Yeah. So in the case I was talking of, I had an issue where I had excessive tailpipe emissions. That's what led the customer to my door. And let's see here. I'm going to pull this up a little bit here. Let me change shares real quick and change PowerPoints. Oops, wrong one.
Kind of like detective work.
Yeah, come on. There, okay, got that. Hate it when things don't want to cooperate. So this happens to be a late OBD1 vehicle. Has a V6 engine, just has to be a GM. And before we get to the car, you probably ask why such an old car. Two reasons. First, the operating theory of the vehicle is still relevant. Second, these cars are still out there. This is a V6 engine, has a mass airflow sensor, bank fired multi-port fuel injection system with one bank of fuel control. So that means that I have one O2 sensor, one set of control, but I fire half the injectors this crankshaft revolution, the other half this crankshaft revolution. So I fire 3 and 3. This is not a sequential system. So this vehicle failed 3 state tests for high NOx. The catalytic converter had already been replaced. They had already done a decarbonization or top end cleaning. The check engine light is off. I found an O2 sensor code in history. And when I ran the Lambda on the tests, the vehicle was failing Lambda. The vehicle was failing and the Lambda was 1.017 all 3 times. However, the one time the vehicle passed at 50 miles an hour, Lambda was at 1.004. So it certainly indicates that Lambda has something to do with the high NOx. We had a code for the O2 sensor, and it really was not it had actually been replaced already, but the O2 sensor was bad. And so I put an O2 sensor and ran another test. And now with the good O2 sensor, Lambda got worse. It went from 1.17, where it had been 1.017, where it had been the last 3 times it was tested, to now I put a new sensor in it. I'm at 1.023. It's even worse. And I double checked and the sensor's good. So here's a car that's already been to other shops, already had a CAT and O2 sensor, already had other parts put on it. I find the new O2 sensor's bad, go through the arguing with the customer that it's new, yada, yada, yada. I put the new O2 sensor in it, and my problem gets worse. The car is actually failing worse now. The emissions are worse. And so what I did is I graphed the data. So what I'm looking at here is I have short-term fuel trim and long-term fuel trim. Now I've relabeled these. These are originally integrator and block learn. And that's why our scale is at 128. So 128 is 0. Below 128 is taking away on time. Above 128 is adding on time. So this is old GM based on computer numbering system of 255, because that's how many numbers you get out of one bit, and half of a bit is a 128. So that's why this used 128, because again, this is old technology. We're really on base computer numbers. But our same rules apply. So 128 is 0. Anything below 128 is taking away injector on time. Anything above 128 is adding injector on time. And what we can see here, I have the engine revved up. I'm looking at the front sensor. And when I came back down to idle, I watched short-term fuel trim go from kind of a normal range all the way down to 72. So 128 to 72 is a little over 50%, little 50 points there. That's a lot of taken away. Now, if you notice what happened is I did this dropped, and then it went back up. Well, look what long-term did. Long-term also went negative. So at the end here, I have 102 on my short term and 113 on my long term. So I'm taking away 15 here, taking away 26 there. I'm taking away 41%. So 41% of on time I'm taking away. But boy, my oxygen sensor sure is switchy nice. So I thought, wait a minute. The O2 sensor is good. I don't have any exhaust leaks. So I know my lambda is correct. We're running lean, and yet it's the computer making the car run lean. So my question was, since I only have one O2 sensor, and the one O2 sensor is on one side, and how this engine works, it has a V6 here, and it has a pipe that comes from this side over to the other side of the engine, has all 3 on this side, and then the O2 sensor is like right here. And so it's like, okay, is it possible I have a balance issue where not all the injectors are working correctly? Okay, possible. How do I prove that? Right? I mean, how can I prove it? And of course, I can go down the rabbit hole. I can get a lab scope on it, and maybe I might see something, but again, I might not. I could disconnect everything to an ohm meter, but that's not really going to tell me anything. I could pull the injectors and do a flow test with the injectors on a bench if I had one, which I don't. I could use a tool that I do have and put a fuel gauge on it and look at the injectors and hit the button, and it turns them on for the exact same amount of time, and I can watch how much they flow. And that would tell me if the injectors flow the same, but my box flows a lot more current than the computer does. And in the past, it's hidden problems on me, so I don't really trust it. And it doesn't trust the rest of the wiring on the computer. And then I thought to myself, wait a minute, I already have some great built-in tools here. I have an O2 sensor that I know is good, and I know the computer's responding to the O2 sensor. So if I disable the injectors one at a time, in theory, should they have the same impact on my short-term and long-term fuel trim? And if I find one that has a lot more impact or a lot less impact, that would be a problem. Is that a reasonable hypothesis? Right? Because all diagnostics is gathering information, analyzing that information, coming up with a hypothesis. In this case, my hypothesis is that all my injectors aren't equal. And then we figure out a way to prove or disprove my hypothesis. That's all we're doing. I mean, really, I mean, I don't care what science you're in. That's analytical thinking. That's how we figure things out. So I think the theory's sound. I think that if I disconnect injectors one at a time, and if I don't see the same amount of change in my short-term and long-term fuel trim, that would certainly be a sign that I have something that's wrong. So I started with the injector that I suspected was my problem based on its location to the O2 sensor, just to see if I was correct. And do you think that injector would be closest or farthest away from the O2 that I would suspect the most? Farthest? Actually, I was thinking closest because everything else is far away. So I was thinking if I have something right next to something, it's going to have more impact than something farther away. And again, I could have been wrong. And I wasn't sure if I was looking for one that flowed too much or didn't flow enough. Right? I'm really not sure what I'm looking for. I'm looking for different. So what I did is I disconnected my injectors one at a time. So now my short-term fuel trim's down here. My long-term is up here. But I disconnect these one at a time. I disconnect the first one, second one, third one. Then I went to the other bank, fourth, five, six. And I went back and disconnected the first one again, just to make sure that it wasn't a fluke, right? Any test you do should have repeatable results, or the results aren't valid, right? I mean, I should get the same result every time. Otherwise, the test results aren't valid. So when I disconnect the first one, not only did I get a lot of positive change on short-term fuel trim, but long-term fuel trim also moved. I also did the other two on that bank. Remember, this is bank fired. So electrically, these three injectors are fired at the same time in parallel. So a problem with one is going to affect what? Current flow with the others, right? So, I mean, because it's an electrical circuit. These three are on the other bank, didn't have as big of effect on it. And again, that's a different bank of fire, and I'm back to one. Also, if we look at the O2 sensor, when I disconnect the first one, look what happened. The O2 sensor went down to, almost zero. And that's what prompted long-term to have to move. The other ones really didn't do that. I got to change here. When I come back to the first one again, I get all the way down really low. So we can really see the instant impact here on the O2 sensor, but that's kind of harder to read, and there's buffering and there's time delay there. But the fuel trim told me exactly what's going on. I have an injector problem that's not flowing. So at that point, I went in and I did actually check the resistance on the injector and found that it was out of specification. And the circuit was okay. But again, kind of interesting how it's in the details. But do you follow the logic I used to get there?
Yeah, so it's the fuel
Kind of a little bit. But what I do, I look for what is not like the others. They should all be the same, right? All my injectors should have the same impact on my fuel trim. So if I disconnect them one at a time, they should have the same result. They're all the same. If they don't, then there's something wrong. I mean, this is a high level concept. I mean, like I said, this is part of the presentation I'll be using again in September. And in my last class, I had people from all over, from internationally on it when I taught this. And I have people going, whoa, you know, this is a new concept to me. But it's really in the same foundation we're learning in this class. What does the fuel trim do? How does it do it? And how can I check to see if it's doing it correctly? So here's another case study I had. This one happened to failed smog, and it failed with high NOx. This happens to be an older Mitsubishi. And I ran a lambda calculation. And what the lambda calculation told me at 1.099 and 1.115, this car's running lean. And just like when we were talking about emissions, if I fail a tailpipe test, and this is a printout from a California smog report, if I fail a tailpipe test, the first thing I do is I take these gas numbers from CO2, O2, hydrocarbons, CO, and NOx and put them in my lambda calculator to see, is the vehicle in fuel control or not in fuel control? If it's not in fuel control, I have to fix fuel control first. In this case, we're clearly not between that 0.98 and that 1.020. I'm way lean. So what I did is I had to ask myself, why would I be running lean? I checked the O2 sensor is telling the computer it's lean. The O2 sensor is buried on the bottom. So the computer is looking at it and it knows it's lean, but yet it's not fixing it. So I got a couple possibilities. I could have a bad fuel pump, but the car runs great. So if the car runs great and goes up hills, could it really be low fuel pressure that's causing me a problem sitting on a dyno at 15 or 25 miles an hour when it goes up the hill at 50, no problem with my foot floored? No, I mean, it just logic says it can't be a fuel pump. It can't be a fuel pump problem. Plus, this was a real pain to check fuel pressure on. So I didn't want to do it, right? I mean, a lot of times our tests are based on what's easy to do. This was hard to do. And so I can do the test blindly, or I can apply logic and exclude it. And in this case, I applied logic. The thing runs great going down the road. It ain't a fuel pump problem. It ain't a plugged filter. So once I really proved in my mind it couldn't be that without any testing other than I drove it and it drove great. And that, you know, people kind of laugh when I go, well, how's the car run? Well, what does that have to do? I'm trying to fix the code. What kind of sets us for what could or couldn't be wrong? So what I did is I thought, okay, going back to what we learned, if the computer is ignoring the oxygen sensor, I'm either not in closed loop or I have another sensor overriding it. Okay. So closed loop, this is an older vehicle, 91. Maybe it wants to be at operating temperature. Maybe it wants some of those things. So I checked, yeah, the car's at operating temperature. Again, I'm looking for that low hanging fruit. Yeah, the car's hot. The electric fan's coming on for the radiators, blowing hot air. We're hot. I have an O2 sensor that I already know is good. I tested it. It can use propane. I can see rich. I can see lean. So I know it's correctly telling the computer. Now we're down to sensor priority. Well, how many sensors does this car have? I have a map sensor. I have a TPS sensor. I have an engine coolant temperature and an air temp sensor. And that's about it. And plus the O2 sensor. So now I'm down to, maybe this one had a mass airflow. I think this did have a mass airflow. But anyhow, I'm down to testing the load sensor and test the other. So I'm going to test whatever's easiest, right? So I test, mass airflow sensor. I'm testing these. I get to the TPS and I test it, and it's in spec at idle, but it's at the low end of it, and it's almost kind of out of spec. And what I noticed is when I raised the engine up to the speed, the 1900, 2000 RPM, I was only seeing 0.7 volts, and that just seemed low to me. And so I adjusted it to read 0.8 volts. As soon as it read 0.8 volts, the car ran clean. You can see how low the emissions got. And lambda now went to 0.999. What happened is the throttle position sensor, the computer saw it at idle and not part throttle, so it didn't have access to the speed and load cells that it can use at part throttle. And it was out of adjustment at idle. So 1/10 of a volt was the difference between this car running clean and this car not running clean. Okay. But again, is this a needle in a haystack? Absolutely. Would most people not have fixed this? Yeah, most people wouldn't have. This car would have gotten a cat, would have gotten a bunch of other stuff and maybe snuck through. But by applying what we talked about in this class, can the computer see what's going on? Is the O2 sensor working correctly? If it's working correctly and the computer is ignoring it, why? Let's look at, are we in closed loop for one? Then look at sensor priority. Why would the computer choose to ignore it? That's what led me to the answer. It wasn't, all my years of experience or anything else, because I'd never seen this before. It was asking the right questions. So that's where that really comes into just that methodical, asking questions, gathering data, asking questions.
Hey, Brian,
Yes.
my problem is what right question to ask. Because
Yes.
I don't know.
No, I agree. And what did I tell you the first week of this class? Didn't I say this class was about learning how to ask questions because I don't have all the answers?
Yes.
So it's all about asking questions.
I appreciate the logic that you're putting it. It's just that my brain is not catching up with your brain logic.
No, but I think we can apply this to a lot of things, not just cars. Right? When things don't make sense, instead of getting frustrated, step back and ask questions. So that was a couple of the case studies I used in this class. So
it is very interesting, and I think it will be very challenging, especially if you know what questions to ask. It's really, really good. I like it.
yeah, no, this was fun. This was actually this class is based on a book I wrote. And so it is fun and it walks through. And the whole premise of the book was that I cannot infuse you with all of my knowledge. So I basically broke emission diagnostics into 3 flowcharts and then expanded each of those 3 flowcharts into basically making yes or no decisions. And so this was, is the vehicle in fuel control? If it's not in fuel control, go to the fuel control chart. Well, that's where I ended up with both those cars, is I had to go to the fuel control chart. And then when I get to the fuel control chart, even though I'm in fuel control, the first thing I have to do is test the oxygen sensor. And then whether it passed or failed. If it failed, put 1 in. If it passed, then I have 2 possible reasons. Either the PCM is ignoring the O2 or the PCM can't control the fuel. And narrows down and do that. So, I mean, this was the premise of the book. And then the last part is if it is in fuel control, then we would go to the emission control chart. And the first step of the emission control chart is to test the O2 sensor, because the O2 sensor is both a fuel control and emission control device. And the catalytic converter won't work right unless the O2 sensor is working right. And we test the catalytic converter early, not to see if it's good or bad and not to replace it, but to see how much of an impact it's having on what we see at the tailpipe to determine how much time I'm going to spend in these other systems looking for a problem. And I break down what maximum emissions are and how much can be equated to what and how much a converter can do and all that. But I really broke it down to 3 charts of do this. And I have a lot of technicians in San Diego County that now follow this procedure because it works. Following this procedure, I've never had a car that I can't fix. I mean, it just was just It's not about being intuitive. It's about making good, disciplined decisions.
This is an excellent reference, Sir Brian. Really, really good because it kind of like shows the logic that you went through each step.
Yeah. So I had a real need, I felt, to share this back in 2012, 2013. And so that's what caused me to spend a lot of weekends putting this together. I really felt a need to share it because I saw so many technicians that I was teaching struggling. Because at the time I was working for a private school and I was teaching both entry level and professional, returning technicians. And I just saw a lot of that frustration and people just making bad decisions. So I'm going to jump back to our other PowerPoint. Well, hopefully that added something to it and didn't just confuse you.
Both.
Both. Well, both's okay. I can deal with both. I didn't want to just confuse you. Come on. Sometimes it gets stuck between the two screens. So fuel trim data is important. That's why they're included in the freeze frame. We talked about the injector on time. So fuel trim is the ability of the computer to deviate from the lookup table or speed and load cells. Low O2 sensor voltage, lean exhaust will result in fuel trim adding, and high O2 sensor voltage will result in fuel trim subtracting. So in this case, we're talking about zirconium. What's that?
Are you sharing something?
Oh, I'm sorry. In my mind.
Yeah.
So in this case, I'm talking about zirconium O2 sensors. Just want to make sure I'm clear. So in this case, even though, and that's what makes O2s confusing. Sometimes we're generically talking O2 air fuel ratio. In this case, we're specifically talking, if I have low O2 voltage, that's a zirconium sensor. I'm going to add fuel trim, high O2 sensor voltage, zirconium sensor, take away fuel trim. So which of the following conditions is required to set a fuel trim related code?
Closed loop.
Closed loop, you got it. Number 2. Absolutely. If fuel trim value is plus 20%, what does this indicate?
Percent more
Is being added, right? And I need to change fuel to on time.
The on time, yeah, the on time, because you can't really say it's running lean because it could be other problems, but you can say what the computer's doing.
Exactly, you got it. I need to change the wording in that question.
You tricked me with the more fuels being.
Yeah, I know I did, and it's my fault. It was not fair.
That was confusing.
Yeah, I know. That's why.
So wait, what's the answer?
Just a second.
More on time.
Okay, thanks.
Number 2, 20% more on time is being added.
Dang, you did that quick on the fly.
I did, and I knew if I didn't do it now, I'd have the same discussion next class. So I was getting it done now. It's a little easier to do in person. In person classes, when we've had a question that doesn't make sense or we don't like it because we're actually using the live responders, I've gone in and edited it with the class to make the question clearer for the point that I'm trying to actually reinforce. which helps that class because they're helping me write the question, helps the next class because the question's better.
And why is number 1 wrong or not correct?
Well, the reason why it's not correct is because just because we're adding injector on time, the whole purpose of adding or subtracting fuel through fuel trim is to keep our oxygen sensor switching above and below 1 lambda. So if my oxygen sensor is switching, I'm not actually running lean. What I'm doing is I'm adding additional on time to get back to stoichiometric. So it's not so the vehicle, so for example, and I have a case study I use this in where I'm actually adding 40% injector on time, but since the computer hasn't run out of fuel control, it has more, and we could prove that by looking at the data. That means that we're still in fuel control because it's still able to switch the oxygen sensor rich, lean, rich, lean. Well, if the oxygen sensor goes rich, we're not really running lean. It's should still be in balance.
So as long as you're in fuel control, you don't say whether it's running, you don't say the car's running lean when you're managing it. It's just that's
right.
in that specific moment in time, it is, but then it's correcting for it. Is that correct?
Exactly. What it's saying is I'm having to open the injector up longer to compensate for what I think is a lean condition or perceive as a lean condition. The problem we have is both in industry and XYZ auto parts, everything else, or chat forums, is they see that 1071 code and say, oh, your car's running lean. Whoa, 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 whoa. Hold on a minute. We've compensated for a perceived lean condition. But unless I'm out of adjustment, we should still be running the stoichiometric. My converter should still be operating properly. Everything should still be working good, even though I've had to work harder to do it. And so that, and the reason why I put that as a wrong answer, because that is a real common misconception of these codes. And it's perpetuated in industry by technicians, by auto parts people, by people doing blogs and people doing videos and all kinds of stuff, and they're flat out wrong. The high fuel trim does not mean the car is running lean. It means it's compensating for a perceived lean condition. But once it's compensated for, we're no longer running lean. We're running stoichiometric. We just had to work harder to do it. And the reason why we set codes is that in theory, if I was using 20% more fuel than I was supposed to, that's going to lower my gas mileage, which increases my grams per mile. Therefore, we turn a check engine light on. So it is the thought of additional fuel being used and lowering our miles per gallon, which increases emissions into the atmosphere, is why we turn the light on for it. We're not turning the light on because the car's running lean. We're turning the light on because we're using more fuel in theory, by holding the injectors open longer than the engineers designed the car to use. And once we get over a certain point, hey, if I'm adding X number or more pounds of fuel to the engine per mile, then how many more grams of hydrocarbon and CO and CO2 and whatever emissions are getting in the air per mile? And that's what triggers the problem. So this is a compensation. If we've compensated correctly, it should be good. No difference than a door, right? If you have I remember going over to Grandpa's house and there was doors that you had to give them a little bit extra to get them to shut, or a little bit extra to get it to open. Well, the door still opens and closes. The door is only stuck until you open it, right? It just took more effort to open it. So similar thing, we wouldn't say, well, the door is stuck. We'd say the door is sticking because I was able to open it. Maybe not the best analogy. Okay, so that is it for fuel trim. A little longer there than I thought we would, but that's fine. Let me get out of this one. Okay, so let's pull up this one. So this is OBD2 scan tool communication, and it's going to introduce us to some terms and also kind of how some of the mechanics work a little bit. And this really goes in conjunction with the video that several of you have already seen. I know there was some confusion because some people didn't read all the instructions to see there was no lab sheet. I got a couple emails on that. Always good to read instructions before you panic. I thought I was being nice not putting a lab sheet in there. Okay, so we talked about hexadecimal already, and that's a scientific numbering based on 16 that I'll show you a little bit more on the next slide. PID, we talked about parameter identification data. Some other terms we use is TID, test identification data, SID, component identification data, and MID, monitor identification. Now, TID, SID, and MID, especially TID and SID, are used throughout the OBD2 system. And that's our addresses. That's what the scan tool is going to without our knowledge. However, when we look at mode 6 data, we will actually use TID, SID, and MID as part of our mode 6 data and part of our interpreting our mode 6 data or looking it up. So these are things we'll actually see. MID is only used on CAN vehicles and allows them to self-ID their tests on any scan tool. The older systems used a TID, test identification data, that was unique to each manufacturer and sometimes unique to each model of that manufacturer. So you had to go look that up or have a resource for that. So 2008 newer, mode 6 became a whole lot more usable. So here is our hexadecimal system. OBD2 uses hexadecimal to communicate and calculate. Hexadecimal is based on 16 with 65,535 possibilities. So that is a common default number we see in computers. So if we see that for a data value, we should instantly be suspect of it. Just as if we see a 255 or a 0 is a data value, we should be suspect of it. So this is how this would work. I've got 0 through 9, then I have A, B, C, D, E, F, then I have 1, 0, 1, 1, 1, 8, 1, 9, 1, A, 1, B, 1, C, 1, D, 1, E, 1, F, and then so on. So there's 4 bits to a nibble. Each bit is a 1 or a 0. 2 nibbles to a byte. And so we look at 2, 0 as 2 and 0, not 20. So our modes of OBD2, we have current data, freeze frame data, confirmed codes, clear emission related data, O2 sensor test results for non-CAN, continuous monitor test results, pending codes, request for control of emission equipment, request for vehicle information, and permanent codes. So these are the same 10 modes that I mentioned in the last presentation. So this is just a quick review slide. This is nice because they're all on one slide, so you can see it. So mode 1, PID 1 is my monitor status since DTC cleared, includes the malfunction indicator light status and the number of DTCs. So remember what I said, everything in OBD2 is all by addresses. Your scan tool, when it wants to know if the mill is on or it wants to know how if the monitors are complete since you cleared the code, knows it needs to go to PID 1's house. If I want to know what the temperature is, that's a different PID. If I want to know, so all these are numbered. Remember what I said, your scan tool is just a dumb address book. So whatever addresses are programmed into the scan tool is what it's able to go in and look for. Not every vehicle has someone home at every address. Some scan tools will look at all the addresses and give you all the information. Other scan tools only stop at 15 addresses. Here's who we're going to go look at. So it really varies a lot. So the number of PIDs varies by vehicle. We can see different PIDs are available in generic OBD2 and the OE or enhanced side. So I'm going to see different PID values based on which side of the computer I'm looking at. The same sensor may display differently in generic OBD2 than on the enhanced side. So for example, my map sensor for Honda displays is inches of mercury on the generic side. That's the only way it displays. On the factory side, it displays, or enhanced side, it displays in inches of mercury and volts. Well, volts is what I need to perform diagnosis. The inches of mercury isn't any help because Honda specs are in volts. So I need to go, if I want to look at that, I need to go to the enhanced side of the computer and get the map sensor in volts so I can make my diagnostic decision. Same sensor, two sides of the computer, but it can be displayed differently. Another example would be my mass airflow sensor on many European cars. European cars on the enhanced side tend to display the mass airflow sensor in kilograms per hour, which is completely useless from a diagnostic standpoint. What I want is grams per second. Well, with generic OBD2, by law, every manufacturer has to display it in grams per second. Now I can use the same trick I use on a Chevy and Ford to diagnose a Mercedes, because now I have a PID that is in the values or in the calibration that my diagnostic tools are designed to operate in. Another issue we have is that on the enhanced side, manufacturers are allowed to lie to you. They're allowed to use what are called substituted values. So in other words, if I unplug a mass airflow sensor, I may still see a value on my scan tool that moves up and down and reacts with it when I speed the engine up and slow the engine down, and it's going to look normal because that is the calculated value that the computer is operating on based on other sensors to build that calculated value. However, on generic, I will see the actual value of the unplugged sensor because they are not allowed to use substituted values in generic. So generic can't lie to me. So that's what I was saying. Even the best scan tool or the best factory scan tool can give you bad information. So it's important to understand who can lie to you and who can't lie to you. So generic may not give me things exactly how I want them. Sometimes it does. It may not give me as much as I want, but what I'm getting is not a lie. If I'm on the enhanced side, they may completely lie to you. I remember years ago, I wasn't sure which connector went to an O2 sensor because they're all four were bunched together. So I said, I know, I'll unplug one and go look at the scan tool and see which sensor came dead. And guess what? They were all still four working just fine, even though I unplugged one of them. And I didn't find out till years later it's because I was on the enhanced side and it was lying to me. If I was on the generic side, I'd have seen it. So our freeze frame data requires a minimum of 8 PIDs be displayed in freeze frame data, although you may get much more. Freeze frame data may vary between generic and the OE or enhanced side of the PCM. Might get different information. Data must be displayed in the same way by all manufacturers in generic freeze frame. In other words, grams per second have to be the same, and so on. What are the 8 required PIDs? Well, I talked about them yesterday. They are my DTC, my engine RPM, my fuel system, open or closed loop, my coolant temperature, my fuel trim, short-term and long-term. If I have 2 banks, I'd see it for both banks, my engine speed, and my engine load or calculated load. So on this vehicle, I can see I'm idling and I'm not really moving. I got 0 miles an hour and I'm at 18% load, so I might even be in park here. I'm at operating temperature, 90 degrees Celsius. My vehicle's in closed loop, means it's looking at the O2 sensors. I have a code for P0171 system to lean. So you see how misleading these code definitions can be, because we know it's not lean, it's a lean correction. And actually I have other captures on this vehicle and I prove that it's actually not running lean. But I'm adding, when I add 15.6 to 25, I'm adding 40.6% injector on time to keep the oxygen sensor switching. And this vehicle hasn't run out of fuel control. because my short term is only 15%. And I know short term doesn't max at 15. Long term is maxed at 25 on this vehicle, but short term has a lot more to go. So since I still am able to make the O2 sensor go rich, lean, rich, lean, rich, lean, I can be in fuel control. I've just had to stand on 40% additional on time to accomplish that. So in this case, I'm looking at a mass airflow sensor vehicle with high fuel trim values at idle. Vacuum leak. Because if it's a mass airflow sensor, my engine speed would be higher and I'd be going down the road. If it was a fuel pump problem, my engine speed would be higher, my vehicle speed would be higher, and my calculated load would be much higher. So the most likely cause is a vacuum leak. Now, is it possible it's a mass airflow sensor? Yeah. Maybe the guy's been driving for the last year and a half with a bad mass airflow sensor and has gone into XYZ Auto Parts and had the code reset 30 times. I've seen that. Mass airflow sensors normally fail at cruise. Well, you keep them in there long enough and they get bad enough, eventually it'll set it idle before it can set anywhere else because it's just that bad. But that's someone kicking the can down the road. That's not a normal failure. But there's a lot of information here to lead me to what I want to test. So my mode 3 confirmed codes, 1 trip codes and confirmed 2 trip codes, codes that may have turned on the mill. If the code in mode 3 is capable of turning on the mill, it is capable of supporting freeze frame data. So like a P0325 code on a Nissan is not capable of turning on the mill. Therefore, you will see that code in mode 3, but you will not see any freeze frame data. You will only see freeze frame data when a code that can turn on the mill matures. So if you go in, that's why it's important to look and see what code's in freeze frame, because that's the code that turned on the mill. And unfortunately on Nissans, this is on the V6s, this was a $700 repair 20 years ago. And people would see this 325 code and an O2 code, and they'd sell both codes to the customer, thinking that I need to fix everything in mode 3 to keep the check engine light off, because no one told us. We didn't know. So a lot of things are learned because the manufacturers didn't tell us. A lot of things, Nissan finally came out with a TSB on it in the early 2000s saying, don't fix the 325 code, it doesn't turn the mill on. Now on the 4 cylinders, there is reasons to fix it, even though it doesn't turn the mill on, because you can't check timing. So it won't let you get into timing check mode with a NOx sensor code. So you're not fixing the code because the light's on, you're fixing the code because you can't check timing, and you can't pass smog unless you can check timing. On the 4 cylinders, the V6s will let you check it. 1519 code, intake manifold runner control malfunction for Ford passenger cars. On the trucks, it turns the check engine light on the passenger cars, it doesn't. Like the Mercury Mystique and other ones that won't turn the light on for this code. But it will on an F-150 with a 4.2 liter, same code. So why is it more important on a truck than it is on a car? I have no idea. How do I know this? Because I understand that in order to turn the check engine light on, it has to be able to set freeze frame. And I worked on a car that I got this P1519 code into mode 3. Check engine light wasn't on and there's no freeze frame. That means what? It's a type C or D code. That wasn't documented in anything I was able to access. Now, some manufacturers like GM, several years did document all their codes and told you what was an A code, what was a B code, what was a C code, what was a D code. But that's the exception. So codes remain even after 3 good trips and the light is turned off because the problem is intermittent or the vehicle has been repaired without the system being reset. That gets into our 40 and 80 trips. And again, if the code will not turn on the mill, no freeze frame for that code can be set. Mode 4 is the preferred method of clearing emissions data if you don't have access to the OE side of the PCM. The reason why I notate that is sometimes on the OE side of the PCM, we can reset individual adaptations or do different things without having to dump the whole memory. Mode 4 may not clear codes that turn the mill on some European vehicles. So early, pre-2000, especially Mercedes, you could not turn the check engine light off on the generic side because they used two modules. They used an engine control module and a diagnostic module. All OBD2 talked to was the engine control module. So when you went in and cleared the code in the engine control module, the next time the key was cycled, and part of the clearing procedure is turn the key off for 10 seconds, turn it back on, the diagnostic module would tap the ECM on the shoulder and say, hey, you forgot this code. And the light would be right back on. So the only way to do this was to have an enhanced scan tool where I could go in and talk to the diagnostic module, clear the diagnostic module code first, then clear the engine control module. And I had to do it all through the enhanced side. And I made a fair amount of money doing this because a lot of shops that were trying to work on Mercedes didn't have a European scan tool. So they'd kind of fix the car, do everything else. They'd come over and I'd get paid to reset the system because they didn't understand what was going on. And I had the tools, so I wasn't telling them. I was just taking their money. Hey, I spent $6,000 on the tool to do this. You know, you own a shop, you have the option of buying the tool or bringing it over to me and paying me to make it go away and happy. Isn't that how life works? That's why there's equipment rental yards and everything else, right? So using mode 4 will clear the data from the following: mode 1 PID1 monitor status, mode 2 freeze frame, mode 3 confirm codes, mode 5 O2 sensor test results, mode 6 non-continuous monitor test results, mode 7 pending and non-confirmed codes. Remember, mode 4 will not clear permanent codes in mode 0A.
That 0A, the permanent thing is, you said it's from what, 2010 or 13 and newer?
10 and newer. 50% of the vehicles in 2010, 99.8% of the vehicles in 2012. So there was a phase-in period between 2010 and 2012. Mode 5 is our oxygen sensor test results, not used by all manufacturers, not used on CAM vehicles. Some manufacturers put their O2 sensor test results in mode 6. Not all tests will set codes. Also, manufacturers were not required to set codes for slow rear O2 sensor operation prior to 2004, but they may display test results. So prior to 2004, we only had to set a code if the rear oxygen sensor wasn't plugged in, circuit test. We didn't have to do a logic test or performance test on it. So there was a lot of cars prior to 2004 that would have emission problems or have other issues from a bad rear O2 sensor. And people are going, well, the light's not on, so it's fine. No, it's not required to test it. You got to go test it. So it's why it's in, the common misconception is OBD2 is so good that it finds all the problems. And that's just not real. It is pretty good. It's way better than working on a pre-OBD2 car as far as the amount of information it gives me. But there's plenty of things that it doesn't find. We just can't assume that it's going to take care of everything for us. So mode 6. So mode 6 is where we're going to spend the majority of the time in this. This displays the results of the non-continuous monitors, breaks monitors down into individual tests. Individual tests relate to a specific code. Individual tests may fail and not set a code. Some tests are to determine if the enable criteria for a monitor has been met. So in other words, I think it was Chrysler had a test. And no, it's Ford, excuse me. Ford had a test that checked to see if there's enough vacuum present to run a test on the EGR system. And if there's not enough vacuum, the test would fail, but we're not going to set a code. We'll just try again later. It just means conditions aren't met right now. So we could have a code that might never run. I mean, a monitor that might never run a self test because it never has enough vacuum to run the test. We have data that test for vacuum failed, but we'd have no code. And at the same time, we'd have a car failing smog because the monitor hasn't completed and the customer's driven at 2,000 miles. So this is really a way, and it really varies by vehicle. Some vehicles support mode 6 really well. Other ones, not so much. But this is a way of kind of dissecting what's happening in order to try to help us make a better diagnostic decision. So our mode 6 terms are TID, SID, MID, which I talked about. TLT is test limit type. Our hexadecimal we talked about already. So when I get data from a mode 6 test, it is going to be displayed in hexadecimal by the computer. Most scan tools today will convert that to raw data on pre-canned vehicles. And I would need to use what's called the manufacturer's conversion factor to convert that raw data to an actual value of amps, ohms, volts, and so on. On canned vehicles, because of MID, not only do they tell you what is being tested, they already perform the manufacturer conversion and give you the actual value of what it is. How much vacuum, how much pressure, how many volts, how many amps. So they're giving you a real number, not only what it got, but what the minimum and maximum values for that test are. So you can see how well it passed or how bad it failed. Gives us our test value, our results, pass or fail. And limit type is kind of a repeat of TLT, but that is there a minimum test or maximum test? So pre-canned vehicles, you either had a minimum test, I can't go below this number, or a max test, I can't go above this number. So if I wanted to test something that can't go below this and can't go above this, I need 2 tests. With CAN, they now have one test that has a real minimum and maximum value, and they're doing it all with one test. So that's another thing that changed with CAN. But again, why is that different? Well, computers were better in 2008 than they were in 1996, right? I mean, you got better computing power. So which monitors are non-continuous? Our converter, fuel evaporation, O2 sensor, O2 heater, air injection, EGR. Some manufacturers put other data in mode 6, such as misfire counters for Ford pre-can, and all CAN vehicles now have misfire counters actually in mode 6 data, which is huge. Thermostat operation, Toyota and Honda. So there is a lot of, and we get into diesels, there's all kinds of diesel information in mode 6. So there's a lot of dissecting. So if I want to look up, there's 2 different ways that people go about mode 6. One is they look everything up ahead of time and then go try to fill out a chart, which is how I was taught to do it. What I do is I go look at the mode 6, go look for anything that looks bad, and then look up what the look bad is. Because if nothing looks bad, why should I waste time looking things up? And I found that to be much more efficient. But in this example here, we're going to look up something for mode 6. I'm on an Odyssey, and I'm going to look up a heated O2 sensor. And it tells me that that's going to be a test ID 1011, and component ID is 85 and 05 respectively. And this is for my front O2 I'm sorry, 85 and 05 respectively. So this is for my front O2 sensor heater. And this is for Odyssey. So this only applies to Odyssey and Pilot. So then I can match this test to specific codes. So in this case, I've got test ID 10, component ID 85. It's a P0135 code. Test ID 11, component ID 5 is also a P0135 code, which is an oxygen sensor heater circuit code. If I look here, it gives me the test description, matches the electrical current of the sensor heater when the heater is on. My measured value is the output value times 26.7 milliamps. My lowest limit is output value times 26.7 milliamps. And my highest is nothing. If I come down here, I'm still doing the same measured value, but now my lowest limit is nothing and my highest limit is here. So this gives me a range. So you can see one of them is looking for a minimum amount of current The other one is looking for a maximum amount of current. What are we doing? We're doing a resistance test of the O2 sensor. If I flow below this current, I have too much resistance. If I flow above this current, I have too little resistance. So we're doing a resistance test by current, amps. So here's another different vehicle. In this case, I have an O2 sensor heater circuit, test ID 4, component ID 2. The scanner captured originally, we used to just get it in hexadecimal. So $2091, and my minimum value was $0A3D. Now, I don't know if that's supposed to be bigger or smaller than that 2091. So we used to have to use a scientific calculator and calculate each of these one at a time. So you only used mode 6 when you were looking for that Hail Mary pass into the end zone with about 2 seconds left on the clock. It was not your first choice. One of the things scan tools started to do is they started displaying, and they still do today, these raw data numbers. So I know 8337 is a lot bigger than 2621. We passed, and we passed by a long way. Next, I really don't care about anything else. So when I'm looking at data, I'm just looking at numbers. Are we close or are we a long ways away? If we're a long ways away, we're good. And if it failed, I'm looking for, obviously, if I had 8336 here, yeah, it passed. I don't have a code, but boy, that's really close to failing. So this allows me, what mode 6 allows me is allows me when I have a code to see potentially how bad it failed. Again, not all codes are supported by mode 6. This is our non-continuous monitors. But like fuel evaporation, how big a leak did I have? Did I have a little leak, or did someone leave something off? Well, the mode 6 test will tell me. So it also could show me after I fix the car and I go run the monitor, I'm going to get new mode 6 data, and then I can see, did I barely fix the car? Yeah, you know what? I put a new part in, and my new part that I got from XYZ Auto Parts tested 8336, tested 2622, and my minimum value is 2621. I'm not feeling real good about this. So you see where this can let me know when I put a part on, is this car really fixed and going away? Did it barely pass, barely fail? So I have a much higher degree of confidence on the success of my repair. Now, if I want to get the actual manufacturer or the actual value for this raw value, this 8337 or this 2621, I would need to convert it by the manufacturer's conversion factor. Now, this factor is different for every manufacturer. This manufacturer is different for every test. So this is, fortunately, now there are scan tools that do this for you on these older vehicles. And newer vehicles, we don't need to do it because it's done automatically as a feature of MID and how a scan tool works today. But here, I need to multiply times 0.000076 amps. So my test value is 0.633 amps, and my minimum value is 0.199 amps. Well, now do I have a real number that I could actually put an amp meter on or do testing with to see what's going on if I wanted? So the manufacturer's conversion factor for me is like a fire extinguisher. You need to know what it is and where it is and hope you never have to use it. Because in reality, we don't use it. On older vehicles, I can count up the number of times I've used the manufacturer conversion factor on one hand. And normally the only time I go there is when the car comes to me and it already has a new computer and it already has a new part and the part tests good. And now I really need to see what the other shop missed. Right? For normal repairs, I am not using the manufacturer's conversion factor because I know 0 is a lot less than 2621. And I know 8337 is a lot bigger than 2621. And that's really all I need to know. So here's another one, the EGR monitor. In this case, we captured some data, and my test value is 96, and my minimum value is 64. So the description of the test is the EGR gas temp increasing value, malfunction, minus the malfunction threshold. So we're looking at how much temperature did did it rise above the minimum? So we're looking for a minimum of 40 centigrade temperature increase. That's our minimum. So if I don't get 40 centigrade temperature increase, we fail. So we're looking at how much better than that did we do. So if I look at this, it's 64 times the conversion factor minus 40 gets me 0. So that is 0 degrees above what my minimum threshold is. When I put the 96 in times the 0.625 equals 60 minus 40, which is 20 degrees centigrade above the minimum. So this is what I was talking about by we're measuring for degraded components. If I was looking for something that's bad would be a 0 degree increase, right? That's broken. That's the kind of things that we would set a code for with OBD1 or pre-OBD2 is just, is it working or is it broken? Now with OBD2, we're really looking at degrees of good. We're looking at because a 40 degrees centigrade change is still a huge temperature change. So the engineers probably figured out that at 40 degree change Celsius, we're still probably going to be able to manage our emissions with the catalytic converter and other things. And that gives the customer time to get the car into the shop and get repaired before we breach that 1.5 times FTP threshold. So the goal here is to try to get the customer in and get it repaired before it's really polluting out the tailpipe. So here's a brief explanation. In this case, the increase in temperature caused by the exhaust gases flowing through the EGR valve must be a minimum of 40 degrees centigrade. This EGR system is causing an increase of 20 degrees centigrade above the minimum. In other words, the increase is 40 plus 20 or 60 degrees centigrade. If the temp increase is too little, it could possibly be caused by a partially plugged EGR port, carbon deposits, a bad valve, a bad signal, any of those things. So this doesn't tell me what's wrong, but what it does tell me specifically is which test failed that's setting the code. So now I know what I need to fix. I need to fix it so I get more heat going through this tube where I have a temperature sensor. Is that by getting the valve to open? Is that by cleaning out the tube? Is that by, maybe I don't have enough back pressure on the exhaust because I'm gonna put an aftermarket exhaust on it, so I'm not flowing enough gas, so I'm not generating enough heat. But at least I can see exactly what caused the computer to fail. I'm not the computer to fail, caused the computer to set the code. So here's an example with a catalytic converter. So catalytic converters are a little bit different in that most manufacturers measure the amount that the catalytic converter has degraded, not how well it's doing. So in this case, a test result of 0 would mean the catalytic converter is working at 100% efficiency. It's great. In this case, my test result is 10. My test limit is 128. So my unit conversion factor in this case is to take my value times 0.0039. So catalyst deterioration level determined by the waveforms of the front Euro 2 sensors and an algorithm that's built into the computer on the vehicle. So here's an example of using mode 6 to determine the actual converter efficiency of the catalytic converter and what the manufacturer feels is minimum acceptable performance. So if I take my 10 times 0.0039, I come up with 0.039 or approximately 4%. If I take the 128, which is my limit, times 0.0039, I come up with a 0.4992. Maximum allowable, approximately 50% of deterioration. So 50% minimum efficiency is allowable. In this case, my converter is working at 96% efficient. So what I've done is I've taken my reading and subtracted it from 100%. By subtracting it from 100%, I come up with my 96% efficient. So this is really neat because I can look at a catalytic converter and see how well it's doing. I can put a replacement catalytic converter on a car and see how well it performs to make sure that it's going to be good for the customer. I can compare how good a replacement converter is on bank 1 compared to the converter on bank 2 that's original to the car and has 200,000 miles on it, right? So is the factory converter at 200,000 miles still working better than the piece of junk that I got from XYZ Auto Parts? Or is the one from XYZ Auto Parts actually doing a good job for me? Because that's going to help me determine how long till the light comes back on. So this is, again, another way I have of really developing and getting that information and kind of looking behind the curtain to see how the computer is making some of these decisions on these non-continuous monitors.
Hey, Brian,
Yes.
this is the test that has a maximum allowable. The other previous test only has minimum, and they
Right.
both pass. So that means the two results are higher than the minimum allowable.
Right. So in this case, because we're measuring the amount that it degrades, if my result is above my maximum, we're saying it degraded more than it's allowed. I could also display the results, and some manufacturers do, is minimum efficiency, where I might start at 255 and I can't go below 128, for an example. And saying that, hey, but for catalytic converters, for some reason, manufacturers tend to measure and display the amount it's degraded, where other things like the EGR were showing how much it's increasing or how much it's doing. So we see some min tests and some max tests, both for performance and also for electrical performance on some things, like we saw the amperage test. So let me pull up a picture of some real mode 6 data off a scan tool here. So here is some real mode 6 data. So this gives me my ECU ID, which happens to be an engine control module, my test ID 0A, and my component ID 00. My minimum allowed is 20. Maximum is NA, so I can be as high as I want. And my test value is 57. And in this example of a min test, the test can't go below the minimum without failing the test. The TID and SID are listed in their hexadecimal number that would have to be looked up in the repair information for this vehicle. Since the test easily passes, there's no need to perform the manufacturer's conversion or to take the raw numbers to actual values. So this is an example of there's nothing wrong here. I'm not going to go look up what this is unless I'm trying to figure out monitors or something else. So there's times I might do it. But this test easily passed. This isn't what's turning the check engine light on. So I really don't need to do anything else with it. Here's an example of a failed test on the same vehicle. So here I have a value of 239 and a maximum allowable of 192. So I have a test ID and component ID, no minimum, maximum 192, and my value is 239. So we failed. So here's an example of a failed mode 6 test. This is a max test, and the test result can't exceed the max number without failing. Although a conversion to raw data numbers to actual values could be done, what's the point? Look up the TID and SID in the repair information and move on to component testing. You're done here. And what I mean by that is that this happens to be for a catalytic converter. But what I mean by that is that even if there's an O2 sensor or an EGR, do I really care that it's not increasing temperature? Say I need 40 degrees increase and I only get 38. Am I really going to go and try to just get 2 degrees more temperature to make it pass? Or I'm going to go diagnose the system and repair the system. And then once the system's repaired, it should have correct performance, whatever the manufacturer designed. So I'm not going to go. So that's another reason why I don't use the manufacturer's conversion factor as a rule, because I'm not going in going, you know what, I just need to get rid of 2 milliamps and this thing will pass. Or, oh man, if I can only get 1 more amp of current in this circuit, then this would pass. What are we going to do? We're going to go in and diagnose the circuit or the system that's failing the test and fix it. And as a result of fixing it, my mode 6 values when I retest should be in the normal range. I can also look at mode 6 in one shot. In this case, I'm in generic. This is a different tool I have. I'm looking at all the mode 6 tests supported. And you can see I can scroll down to more. And this tool isn't telling me what these are, but it will tell me this one failed and these are close to failing, and I might want to do more investigation. Now this tool has the feature that if I click on this, it comes to a drop-down menu. And if I tell it what kind of car it's working on, it decodes everything for me. So I bought this tool. One of the main reasons why I bought this tool was for this feature. So I went out and bought a scan tool just because it does this feature and a couple other ones. That's what initiated me to buy the tool.
Brian,
It's because I was doing so much of this work. Yeah.
Not all technicians or chefs may have the sophisticated tools that you have. And how will they kind of know this?
Right. Well, this tool here is giving me the same information. The difference is I'd have to go into each page to get the information, where with this tool, I can get it all on one page. It's the same information. So, I mean, there are some $100 tools, $120 tools that'll give me mode 6 data. I'm going to be looking at it one piece at a time. It's going to take me a while to look at it. But there are inexpensive tools out there that do support mode 6. I spent the money on this tool because in the shop, time is money. So if I instead of spending 20 minutes looking at all this, if I can look at it in a minute, that makes sense. That justifies the tool in the shop. You know, but you know, if I just need the information, I'm limited to the tools I have. And that's why I show pictures of different tools, not just tools like this of, oh, this is the only way you can look at it. It's just, it's a different way of looking at it. Same information. So the big difference in tools, especially with generic OBD2, to a certain amount is how many of the modes it's going to support. But once it supports a mode, for example, I have a small code reader about this big and it supports mode 6. I think retail on it was $100, $120. I got 2 of them. I won them both, 2 different places. I keep winning the same thing, right? And I keep one in the glove box of my car. And I had one here at the house when I worked at the shop, and I'd use it if I had a problem with my house or my dad had a problem with his truck, because I could come over and I could do some preliminary diagnosis with the tool. And it's not a bad little tool. And it supports mode 6. So I can go in and look at these tests, but I'm looking at a screen this big and I'm looking at them one at a time. So if I'm trying to make a living, that's not going to be real efficient for me to look at, what do I got, 40 tests here? So again, it really varies by the tool and accessibility. But that's why it's important to know what's in the modes, because if I know what's in the mode and know what's supported, then I know what information I should be able to get there. I mean, I have tools at home that I do stuff with, and I have friends that are contractors or plumbers or electricians. They have better tools because they do it every day. I can still do the same job, but what takes them 15 minutes takes me an hour and a half, right? That's the difference, but it doesn't justify for me necessarily buying the tool they use. I only do it, once a year. I'm not going to go buy the super duper whatever. So mode 6 at a glance. So this happens to be a Toyota, and Toyota happens, this is pre-CAN. So this vehicle supports these test IDs, only 5 of them. Very different than the Nissan example on the previous slide. And when I go into test ID 1, which happens to be for the Cali converter, I have a little thing that slides up and down here between component 1 and component 2. Component 1 is bank 1 converter. Component 2 is bank 2 converter. And I can see here that my bank 2 converter failed. I was allowed a max of 128 and a value that I got during testing of 131. So this thing barely failed. That's a plausible result. Time to go test the Cali converter, time to go test for exhaust leaks, O2 sensors, all that stuff. What I do know is that the Cali converter is not hollow. I know it's not completely dead. And I need to make sure that it's not something like an exhaust leak or an O2 sensor or fuel trim problems affecting the converter's efficiency, that maybe if I fix those, now the converter is going to test good and not need to be replaced. So mode 6, I mean, we could do a 7-hour class on mode 6. I mean, so I don't feel bad that you're going, man, that was a lot. The purpose of this class and the purpose of the class at ECC is to introduce you to a lot of these things. become familiar with the concept and become familiar with what it is, not necessarily make you a practicing expert at it. So I don't want you feeling overwhelmed that, man, that was a lot and I'm never going to be able to do this. Again, it's about asking questions. So at least now you know that there's this feature in there that if someone says, oh, you need a catalytic converter, you can go, well, how were the test results when the computer tested it to get my 420 code? If the person gives you a blank look, maybe you shouldn't be going to that mechanic, because that clearly shows that they don't know how to get the test results. So what they do, pull your 420 code and tell you need a catalytic converter? Right? I mean, seriously. So now you know what questions to ask. Oh, well, okay. So I got the 420 code. Well, how bad's the test results on it? What's going on? Then I can look at freeze frame. Well, when did the code set? Going down the highway, go around town, accelerate, decelerate. I mean, I can get a lot of information here, so I can kind of go, okay, well, what's really going on? My dad's truck for the last 3 years is set a catalytic converter code for one of his catalytic converters only when he's driving to Mammoth. Long highway during the test, eventually kicks it and it fails it. And it fails it like this, 131 to 128, barely fails it. On one bank, he has 400,000 miles on this truck, original cats. I tell him, okay, let me clear it because I can see where it failed. You told me the light came on when you're on your trip. I can see where on your trip you were at. Let me clear it, see if it comes back around town. Sure enough, never comes back. Next year, he goes to Mammoth because he has a cabin up there. And I get a phone call from him when he gets to Mammoth that the check engine light came on. Does it once a year. I'm not putting a, several $100 catalytic converter on his truck because it hiccups once a year on a long trip going up to 395.
And is that, you said that's a 420 code?
Yeah, 420 code, 420, 421, 430, 431. Those are all the cat efficiency codes.
So that's, but the 420 is below, correct?
Yeah, all 4 of those are for below efficiency. 420 is bank 1 converter below efficiency. 421 is bank 1 pre-converter or warm-up catalyst, warm-up catalyst below efficiency. 430 is bank 2 converter below efficiency, and 431 is bank 2 warm-up converter below efficiency. So those are the 4 cat codes. They all are saying the same thing. Normally, with very few exceptions, you either get a 420 or a 421. You don't get both options on a vehicle, so they're either monitoring the warm-up cat or they're calling the warm-up cat their main cat. So it gets into a numbering thing. Very few cars, Volkswagen's one of them, that actually monitors the warm-up cat and the main cat separately. So they are, and that's only on a couple models. So normally, you'd want to treat a P0421 the same way you treat a P0420. They're both saying the bank 1 converter that is being monitored is not working at correct efficiency.
And that could that be because possibly it's either I don't know, like clogged, saturated, or something like that, like with carbon, stuff like that. So yeah. on the higher mileage trips, the further it goes, the hotter the cat gets, the harder it, and the less efficient it's able to store and release that cerium as possible. I mean, the cerium stores and release the oxygen. Is that possibly a reason why it sets the codes only on those long trips?
Odds are it's not the cat itself. Odds are it's an O2 sensor that's getting tired after working for a few hours. Because the chemical reaction inside the catalytic converter is fairly consistent based on fuel control, based on lambda. But since we're using the O2 sensors to test it, and we're using the O2 sensor to control fuel, if I have an O2 sensor that's getting hot after a couple hours going across the Mojave Desert when it's 110, it may decide that, you know what, I'm just really feeling lazy. It's hot under here. And so that could affect the switching. And as we affect the switching, it can cause the cat not to work correctly. Now, keep in mind, prior to 2008, O2 sensors were only tested once per warm-up cycle. So that O2 sensor would get tested within the first 20 minutes of operation, normally in the first 10, and then we're just going to believe everything it tells us for the next 4 hours of driving. Where the catalytic converter monitor is tested at different times or further on during the drive process. So that's another reason why we might see that, is it on those vehicles, because this is a pre-2008 vehicle, that I have a sensor that's getting tired, after working for a while. Electrically, it's, has an issue, but yet we're not setting a code for it. So I'm of the belief that, if it happens, if it only happened on your trip, let's clear it and see if it happens again around here. If it happens again around here, now we'll spend some time diagnosing it and putting parts on it. But if it's something that happened on your trip and your car's running fine, and that was on the first day of your trip and it was a 1 or 2 week trip or whatever, I am just not going down the rabbit hole on that. I'm just not that concerned about it. And that would be true if it was a customer's car. And so it's not just a matter of my dad's car and trying to help him out. I'd be the same way on a customer's car. I'd inform them, but I'd tell them, hey, here's what the computer saw. Here's what's going on. Right now, everything's testing good, or it's testing weak, or whatever, however it is doing. Here's your choices. I can throw one on. You can take it, drive it. If the light comes back on driving around town, we are going to need to do it because it does test weak. If the light doesn't come back on, have a nice day. And I think a lot of customers appreciate that honesty. Because that way the customer knows if the light comes back on, they know they're probably coming in and buying a catalytic converter. I mean, because I've already done all the testing, I've already done all that. They're not mad that the light's back on, but they know that I was reasonable. I know that I was using common sense, not just trying to sell them another cat.
Sir Brian,
Yes.
are these values affected by elevation or weather conditions such as summer versus winter?
Yes, absolutely. So anything that affects the vehicle can affect the test results. That's why we have enable criteria, right? So certain tests won't run above 8,600 feet and so on. So we have enable criteria, temperature criteria. But even within that range, I know I feel very different when it's 50 out than when it's 90 out, right? I work differently. Certainly our cars work differently also. So as we change altitude, as we change range, we do get variance in there. So something that may fail at 4,000 feet might be fine all day long at sea level. So we do see some of that. And that's also why I go back to that trip analogy. It happened on your trip. Is this just something that happened because you were doing something you don't normally do, or is the vehicle actually broken? So yeah, it will affect, especially when you're looking how I drive the car when the test is performed can affect the outcome. So I might drive it in a way that it encourages a better outcome than how the customer might drive it normally. Or I might, drive it in a way that discourages an outcome and prevents it from running. So for example, the monitor for the oxygen sensors on my Toyota will run between like 20 and 70 miles an hour. So just for fun one night coming home from San Diego, and this was at 10:30 at night, I said, I wonder if I get on the freeway and keep the speed above 70, if I can keep the O2 sensor monitor from running. And sure enough, all the way from Mission Gorge, all the way to Fallbrook, that monitor would not run. When I got off the freeway in Fallbrook and started driving on the road here in Fallbrook, it probably ran within a quarter of a mile. So I was able to keep it from running by being over 70 miles an hour, which is what the enable criteria said. So certainly, yeah, our driving can definitely affect, whether it runs or not, but also affect the results based on what we're doing. My converter is going to, look different If I have a truck that's full than if I have a truck that's empty. My calculated load's going to be different. So even though I have a range that I'm allowed to test, if I'm at 20% versus 60%, we're probably putting different emissions into the cat that could affect the result on the cat.
When do we know when it's a problem that we need to bring it to the shop or we need to check something else?
I'm sorry, I didn't get all that. Is it a problem when?
When do we know if that is the case? You know, sometimes it's affected by elevation, by weather condition, by the way we're driving, and something lights up. When do we know that it's a problem that we need to bring the car to the shop or we need to test something else?
Okay, so anytime the check engine light comes on, there's a problem. Keep in mind, many of these are 2-trip codes. So what we really want to do is we want to put that problem into perspective. So even when that comes in, I'm still doing direct testing on it. But if it tests okay or it tests good, then I need to think of, or if it tests marginal, which is a lot of the case, it tests in that weak area, right? Yeah, it's not great, but it's not horrible. Well, do we really want to replace it just because it's not great? That's when we might want to ask is, did this just come on because I was on vacation? Or did this come on my normal drive to and from work? If it's on my normal drive to and from work, I probably need to get that fixed now. If this is, I've never had a problem and I was on a long trip and it only did it the first day of the trip and it hasn't had a problem since, and the light went out on its own, and I'm pulling this out of history, that's going to be a different thing because the computer already says, hey, we've had 3 good trips where, you know, whatever it is intermittent. So that's why those things are built into OBD2. So I can look at how many, on a newer vehicle, I can see how many miles it's been driven since the code set or since codes were cleared, how many times the car's been started. I can look at a lot of data to figure out, you know, what's going on here and how to address. And that's why we take our car to a shop and have a trained professional look at those things. You know, what you need to do is make sure that the person you're taking it to is a trained professional and that they are, you know, doing their due diligence. No different than if I was going to a doctor, you know, we normally kind of like, what medical school did you go to? Have you ever done this operation before? You know, we would ask those questions. But somehow when we get to mechanics, it's like they're all the same. I mean, how many of you have ever asked, is your mechanic ASE certified? What areas is he certified in? What licenses does he hold? What kind of education did he get? We just assume that anyone back there is capable of putting the parts on our car and doing it well. We wouldn't do that if we were getting eye surgery, right? I bet you if you're gonna go get laser eye surgery, you're gonna ask a couple questions. I'm just guessing. I know I would be. Thought of laser eye surgery terrifies me. We all have our things, right? So mode 7 is our pending codes. Monitor failed the first trip, flashing mill, no code set. Some codes will only display in mode 7 and stay there because they're not emission codes. This is a manufacturing glitch. Example is a P0463 for the fuel sensor malfunction on GM prior to 2006. But it will keep the fuel evaporation self-test from completing because it doesn't know how much gas is in the car. Mode 9, and I have this, I'm not going to read through this whole thing, but these right here are our different TIDs in mode 9. So mode 9, TID 3, mode 9, TID 4, and so on. Not all these are currently supported or supported by all cars. There's a couple things in here that are really helpful that are supported. So one is the VIN number, required to be supported on all light duty vehicles from 2005, although many manufacturers supported it earlier. Our software calibration or version number, my CalVid or calibration verification ID, CVN, and my in-use performance tracking, which I'm going to take a minute and explain. So as I look here, what's that?
I don't have mod 8 because
mode 8, I skipped a slide. Mode 8 is bidirectional controls that don't work, were never implemented, and you want bidirectional controls, you need an handle. So I skipped it based on time because I'd already mentioned that. Boy, I'm being held to the fire today, I tell you. So we can see I can request control of mode 8 is request control of onboard systems. Again, I've never had it work. I've had a couple of people say some things have worked. You got to go to the enhanced side if you want that. So read vehicle identification. That's what I have the screen right here. So I have my VIN number, my calibration identification, my calibration verification number, and my ECU's acronym and test name. So here's a VIN. Tells me what computer I'm in. Tells me this computer, E8, is the ECM for engine control. Here's my calibration numbers, and here's my calibration verification. So if we are looking to see if there's a recall or a TSB where I need new software, these are the numbers I'd look at to see, do I have the newest version of software or not? So this is my software. My in-use performance tracking, or IPT data, monitors how many times we've started the car and how many times we've met OBD2 monitoring conditions. This is not cleared with a scan tool. The only way this is cleared is by disconnecting the battery. So on this vehicle, which I think this was a 2010 or is this 2012? I can't remember which. Doesn't matter. But the engine starts at 2,700, but it only met monitoring conditions 1,073 times. When I look at the catalyst monitor, it met the conditions to run the monitor 1,073 times, but it completed it 1,209, meaning it completed it, has the ability to complete it more than once per warm-up cycle, which means this is newer than 2008. Prior to 2008, the completed will always be lower than the condition. If I look at my EGR monitor, we had conditions 1,000 times, but ran it 2,100 times, almost 2,200. So almost twice as many times as we were able to. My fuel evaporation monitor met the conditions 728 times. The fuel evaporation monitor is the hardest to meet the conditions for. It completed it 399 times, and this is the 2012 vehicle, only 16 months old. You still see the evap monitors completed a lot fewer times than the monitor conditions have met. But still keep in mind that 399 completions is almost once a day the monitor is completed. And the monitor on this vehicle runs key off overnight. So, which is one of the goals EPA had, was to run the evap monitor more and more often. So we use in-use performance tracking data. I can tell how many times the test has been run. So like on the catalytic converter, if I clear the code, I can see what the IPT data shows. And then the light comes back on. I can go and see how many times did it actually take to test it before it failed. Was it 2 times or was it 40 times or 30 times? All CAN vehicles support IPT data. IPT data is only supported on CAN vehicles. And so this is one of the newest things. And this is all based on ratios. So I also use this on cars that might not have monitors complete for the purpose of a smog inspection. So I can go in and look to see, is the ratio within the acceptable limits? Because if it's not, then I know the car has a problem. If it is, it probably just either has a new problem or hasn't run this time. So I can use this to kind of help decipher long-standing problems or programming issues with vehicles. So this is our in-use performance tracking. So this is, again, kind of a behind-the-scenes tool. How many times are we meeting the enabling criteria to run the monitor? How many times do we actually complete the monitor? And then we have our permanent codes that can be confirmed. Can't be erased by a scan tool, generic ROE, can't be erased by disconnecting the battery, can only be erased by the PCM once it is satisfied the system is working properly. Codes in mode 08 will not turn on or keep on the check engine light or MIL. Some manufacturers have a special drive cycle to clear permanent codes. For example, Toyota, after you run the monitors, requires you to idle for 5 minutes in gear to clear the permanent code. If you just shut the car off without the idle period, it won't clear the code. And I discovered that by accident before I saw the TSB. But the goes in. So that's permanent code. So that's all of our modes and what I see on a scan tool. What I did put in here, and I'm not going to go over it in class, but I do want to point out because we're out of time, OBD2 diagnosis. So I talk a little bit about the check is to kind of do things the same way every time. And I walk you through the modes here of gathering information. And there's about 7 slides here. So it's not real big, but this is up in Canvas. This PowerPoint is, so you can get it. It's a PDF, you can download it. But this, again, is kind of that step-by-step of, we learned about all these modes. How am I going to go through and work and gather that information? So I talk about grabbing monitor status. Well, why do I care about monitor status if I'm not smogging the car? Well, the monitors should always be complete. So if they're not complete, that means someone has erased the memory on the vehicle, which means I need to be suspect of the other data. There's missing pieces. There's things that haven't been tested. Someone's tried to fix this car before I got to it because the monitors aren't complete. Because under normal conditions, I go out to any of my cars, the monitors are all complete because they stay complete until someone makes them not complete once they've run the first time after a battery disconnect or a code clear. So, you know, if you haven't had the battery disconnected or the code cleared in a year, guess what? All your monitors should be complete. So if I go and look at your car and monitors aren't complete, I've had help fixing the car. I want to know that. I want to know that early. I want to know what hasn't been tested. Also, my mode 5 and mode 6 data might not be valid. I might have some substituted values. So I need to be very much more suspicious of things because I've had help fixing the car that someone didn't tell me about. So that's why I have you. So a lot of this is just kind of walking through. Is the mill on? Mode 3 confirmed codes. Record all the codes. And again, even if the mill's not on, we still want to look in mode 3. Then if I have codes mode 3, hey, freeze frame is next. And we talk about this a bit. Hey, mode 7, pending codes. And then based on that information, maybe I'm going to get into mode 6 and look at mode 6. Hail Mary, I may need to get to with mode 5 if I haven't found anything on some of these early vehicles, especially some of the Asian imports. And then don't forget about 0A on 2010 and newer cars. So it's just kind of a catch-all to kind of, you know, not forget things. So I got one other thing I'm going to share real quick. Let me stop this share. Since we're talking about catalytic converters, and I do have this video up, I'm going to share. See, escape. Okay. I can close that. There we go. Okay, so let me share the screen. So what I have is I have a Toyota that came in, and it actually has a P0420 code for catalytic converter bank 1 low efficiency. And what I discovered during my testing is my rear O2 sensor was low. It was low all the time. And when I went to test it with propane to see if I had a bad sensor, I was able to get the sensor to move and prove the sensor's good. So my rear sensor is up here in the upper right. And it's just buried at the bottom right here. And so I'm going to show you what I do here is I'm looking for the problem and found the problem. Come on, play. So here's my rear sensor, and we can see that it is just on the bottom. And I found an exhaust leak right next to the oxygen sensor. So this little exhaust leak right here. So I take a rubber hose, cover it up, and we can see as soon as I cover it up, instantly the sensor rises, telling me that 2 things. First of all, that the catalytic converter is oxidizing because catalytic converters are a net user of oxygen. So I'm really looking for that to go up to the rich side. The other it proves is that that little hole is pulling air in from the outside, not just letting exhaust go out. It creates a Venturi effect and pulls exhaust in. It also on the flow. The other thing it does, because of the pulses, every time my exhaust valve opens up, I get a pulse of pressure. When the exhaust valve closes, it pulls back a little bit, a slight vacuum, and that's normal. And that slight vacuum allows me to pull air in from the outside. So this truck that was older, had high miles on it, had a code for the catalytic converter. When I welded up that little hole, cleared the codes, went out and drove it, the catalytic converter tested great. And the car didn't need a catalytic converter. So there is a vehicle that's a nice example of a car that had a P0420 code for low catalytic converter efficiency, didn't need a catalytic converter. Actually, this car had 2 catalytic converters in series. People try to replace them both at the same time because they're tested together. And all it needed was a hole, basically about the size of the end of my pen, welded up. Did that customer get good value for their diagnostic dollar on that P0420 code? Because if they just put a catalytic converter in it, guess what? They'd still have the code. So this, I do have this up on my YouTube channel, this video, if you want to see it again. And it has the audio that I recorded. I have it muted for the PowerPoint talking about it. But just a quick video.
How did you find the tiny hole, Sir Brian? How did you find the tiny hole?
How did I find the tiny hole? With my visual inspection. So there are other ways I can find tiny holes. So I'll show you a different slide here. Get my mouse to cooperate. So another way we have is we use smoke. So I can introduce smoke into the exhaust system to look for a tiny hole. And let me find, I have a picture of doing that. There it is. So this right here was a vehicle that came from another shop. And they checked it for exhaust leaks. It was failing for high NOx. Lambda said it's running lean. The catalytic converter wasn't working right. Lambda really wasn't off that much. But it was, I don't care what the other shop says. I'm testing it. So I injected smoke using a smoke machine into the exhaust system by removing the O2 sensor, and I have an adapter that goes in there. And we can see the smoke billowing out of this crack between the exhaust manifold and the engine block where you can't see. So that's how I found it on that one. And it was just a real small crack. That's what was causing the car to fail. This car had a lot of new parts on it, including a new catalytic converter, but it still wouldn't pass smog. I got it from another shop. But going through the step process I explained earlier, where it's this, and then this, and then this, you don't miss it because this is from that presentation. First thing I do if I have lean numbers on a Lambda or I don't trust thing is test for exhaust leaks. Right? So if you follow the steps, you don't miss the needle in the haystack. It's all about discipline.
Is there any limit to what can be welded in this case, like in terms of size?
Not really. I mean, there is materials, obviously, you don't want to weld or things like that. But I've welded some pretty big cracks down things. It's all about whether you can get in there and get a good enough weld to seal it. And sometimes that's really hard, especially if your crack is more towards the inside here and not the outside, being able to get it welded up and sealed. But I've fixed a lot of ugly stuff.
I have an exhaust manifold that is cracked just before the oxygen sensor. I'm surprised. How does this car even pass smog? And it's been passing. So, and my mechanic at the time said it's too big of a crack to weld. So
yeah, I'm not buying that. You know, if it's a cast iron, I'm not going to weld cast iron. But if it's a tubular steel manifold like this one is, shoot, I weld the heck out of it.
okay.
I mean, I've welded stuff that's like 4 or 5 inches long. I mean, I'm not shy.
Okay, thank you. So
So
I
we
should look
cannot
for a
weld
second
iron?
opinion.
What's that, Branko?
I said I should look for a second opinion on the weld.
Yeah, absolutely. At least take a second opinion on it. You know, some manifolds, like some of the Hondas, are dual manifolds where they have an inside and outside layer with an air gap in between. You really can't weld those because of the design of the manifold. Because if you're getting exhaust out, it's had to go through 2 layers, so it's compromised. You need to replace it. There is some stuff like that out there, but as far as the length of the crack, that doesn't deter me. You know, I mean, I've built a lot of exhaust systems. I've welded a lot of stuff. So, you know, back in the day, we used to say we could weld tinfoil, and that's back when we gas welded everything. I mean, I got pretty good at welding some pretty thin stuff.
Thank you.
And again, it's not a structural weld for the most part. We're trying to what? Seal it. It's not a structural crack most of the time, unless you have bad motor mounts or something pulling on something. Normally it's a heat crack. The metal's crystallized some. So, you know, it's just a matter of controlling the heat on the weld, and you can weld over a lot of that stuff. Cynthia, you had something.
I was wondering why we cannot weld iron. you mentioned if it's iron, you cannot weld it.
Yeah, cast iron does not weld well. So it's normally not welded. It can be, but it's normally not. You really need to heat it up in an oven to get it up to temperature to get good penetration on the weld because of the mass. You can heat it some with a torch. I have done so well, but cast iron flows very differently than steel does and has air pockets in it. So it's a very different characteristic. So cast iron is normally not welded. Normally cast iron is just replaced, and certainly if cast iron breaks into, it's just replaced. So not that it physically can't be done, it's just normally not done.
Mhm.
So, and it's never as strong with cast iron after a weld, but yeah, you know, I have done it. You can do it. There's some special procedures for it. So on that note, so did I make everyone's head explode today? Good. So tomorrow we're going to get into emissions, and we're going to talk about some of these systems like EGR and PCV and thermostatic air cleaner that I've been alluding to here, and kind of say we test them, but I haven't explained what they are and how they work. So we're going to get into our emission systems in module 12, I take a look at what I've opened up in module 12. I have a couple assignments in there, one chapter assignment and one other article reading assignment that has questions attached to it. And then, so there's only one chapter in CDX. The other one's a handout I have. And then some videos. And I think, especially the diagnosing a misfire video, and it's pretty easy. You just got to tell me what I found at the end. I don't even have a lab sheet with it. The idea is kind of enjoy and learn with it. So I think some of you will really enjoy that one also.
Mr. Brand, one last question about that welding. So for example, if someone tries to weld something and it cracks again, are we worse off than where we started, or are we at basically the same point?
Most of the time, we're basically at the same point. It depends on why it cracks again. If it cracked again because they damaged the metal during the weld, either with too much heat, something like that, you can kind of be a little bit worse off. But again, you got a cracked manifold now. So what, you got another cracked manifold. The repair is the same, right? You're replacing the manifold, whether you do it now or whether you do it after it cracks again. Many times where it cracks, it doesn't crack on the weld, it cracks where the metal goes against the weld is where you see the next crack. And you can actually just lay another bead right along that where you're welding the weld to the side that's broken. You just weld across the new crack. And so when something like that happens, a lot of times what you do is you lay the bead across the crack there, and then you lay another one over and then over top, and you kind of bridge it out farther because the metal right next to the crack is the metal that's weak. So by spreading it out through a couple passes, now I can spread that stress out and also the heat dissipation out over a bigger area, which normally keeps it from cracking again. So you don't want to just grind it and just make one little squiggly line. Like if I'm cracking an exhaust manifold, I'll lay one line down and then I'll lay a line on each side. So there's a minimum of 3 lines I'm welding. One that's the actual crack, and then one on each side of the crack to tie my weld in to an area that's further away from the metal that failed.
That is so interesting. Okay. The problem with this is the catalytic converter and the exhaust manifold all in one. So, you know, it's an expensive part to replace altogether.
Right.
So you want to try to,
yeah,
I want to try
Honda,
to fix.
is it a Honda catapult?
Yeah,
or Toyota?
correct.
Honda.
Yeah,
Honda's cracked pretty regularly. Those catapults are available aftermarket. Magnaflow sells them that are approved for California. Walker might have them also. So you don't have to get it from the dealer. They are available aftermarket, but it's still a pricey repair, and it's a common failure right by the O2 sensor there.
Yeah, exactly. Thank you so much for that input.
Not a problem.
Brian,
Yes.
if it's a very small hole, can we just solder it rather than weld it? I cannot handle welding.
Can I do what instead of weld it?
Soldering rather than welding.
Solder it? No, you can't solder it. The heat, first of all, is much hotter than what the solder. You just liquefy the solder, and solder doesn't really join things together the way welding does. Solder goes on top of where weld goes in. Where weld, you're actually taking the material from each side and actually bringing it together. So, you know, I can actually weld things with a gas without even having to add any other material to it if I have good material. So like in the exhaust business, just for fun, because you're doing a lot, you get bored. So then you just find things to challenge you. We take two new pieces of pipe, and one piece of pipe would slide into the other, and you would weld around the pipe. Well, you'd only feed a piece of rod in, and you melt the rod, and you mix the rod with the pipe here and the inside pipe, and you're mixing the metal. You're actually mixing the atoms together and going well. What we'd do is we would actually take these two pieces of pipe, not use any rod, and just get them flowing together and make a nice weld. So with welding, you're actually flowing the metal that you are attaching, not just the rod, but also the metal you're attaching to. You're turning that metal into liquid. Soldering, you're not doing that. Soldering, you're turning the solder into liquid, and it is being adhered to a metal that is not being turned to a liquid. So that's kind of the big, overly simplified difference between like a solder or a braze and a weld.
Okay.